Welcome back. So where I left off, I was hopefully trying to give you an intuition of this inward acceleration. And in this case, I have a rock spinning around, and I'm holding it on a string. And I want to think about what the inward acceleration is dependent on. And so we talked a little bit about its velocity, and these multiple red arrows, these are potential velocity vectors. And the point I was trying to make is, if the velocity vector is bigger, right? To change its direction requires even more acceleration, right? Because the change in the x direction is bigger, and then the change in the y direction is bigger. Because, for example, right here it's y velocity. I'll draw it in a different color. It's y velocity vector, and I'll do it for the big velocity. Its y velocity vector was here, and then now its y velocity vector is this almost essentially the whole vector, right? So when the velocity increase, and let's say, so this is the case of the big arrow. If the velocity was less, like the small arrow, its velocity vector was here, and it would have to go to here. And so I don't know if it's completely obvious, but the change in velocity, for example, in the y direction over this course of time has to be more. And likewise, the change in x direction over this, and that might be obvious, more obvious, because here this is the x velocity vector for if the velocity was less, and this is the x velocity vector if it was more. And that's going to 0 between when the dot goes from here to here. Here it has no x component, right? So clearly, I would have had to decelerate in the x direction more if we have a larger velocity vector. I'm either giving you intuition or I'm confusing you, but I'll keep going. So velocity, clearly, the greater the velocity, the more I'm going to have to pull in on this, the more the inward acceleration has to be to kind of keep this thing going in a circle. And not only does the acceleration have to be bigger just to get that velocity vector down, but you got to realize between this point and this point, the faster I go, the less time it's going to take me to get from here to here, right? So not only am I going to have to change the velocity more, I have to do that in less time. So it's kind of the velocity is affecting this acceleration that I need to pull in two ways. So the higher the velocity, I have to change more velocity, and I have to do it in less time. And it actually turns out that the acceleration is proportional to the velocity squared. And then there's another term here, and I won't prove it in this video. I'm going to prove it in another video that might be out of your scope just now because it requires some calculus. But I want to give you an intuition. So we know that the acceleration is dependent on the velocity squared. And I want to make that point of why it's not just the velocity, because there's two ways that the velocity is affecting is affecting how much of acceleration I need. One is just the magnitude of the velocity. The more that is, the more I have to accelerate to change its direction. And the second is, between this point and this point, I have less time to change that velocity. So the velocity affects it in two ways, and that's where you get an intuition for the v squared. The other thing that matters is actually the radius. So let's say that this is the radius. And the acceleration is inversely proportional to the radius. And why is that? Well, it's kind of like the second, I guess we could call it velocity argument I gave. The bigger the radius, so let's say that let's look at this radius and let's look at another radius that is bigger. Let's say that this is another radius. Let's say if the string was longer and that this was another case. Let's say this is a case. But the velocity was the same. So this is just a case with a larger radius. Whoops. So let's say it's the same velocity vector. So we have the same thing at play. To go from there to, say, there, we have to change the velocity the same magnitude, right? As we had to change the velocity from here to here. But one thing changes. This distance is longer, right? So if this velocity is the same as this velocity, but this distance is longer, you have more time to change the velocity. So the larger the radius, the more time you have to change the velocity, and so the less acceleration you need. Hopefully that makes sense. I don't know if it completely. Let me repeat it, just because I think it's nice to have the intuition. Between this point and this point, let's say when you have a smaller radius, if I want to change the acceleration vector from that to that, I have however long it takes to go this distance, I have that long to change its acceleration vector, its velocity vector. But if the radius was a little longer, and I had the same velocity, so here the velocity is that, and then here the velocity is that, I have a little bit more time to change its velocity. And remember, acceleration is just change in velocity over change in time. And so if I have the same change in velocity, but I have more time to do it with, so if this is a bigger number, the required acceleration is less. So maybe I've given you intuition, and I will prove this for sure because this was kind of a very touchy, this is a very kind of soft way and not very rigorous way of proving that the required acceleration to make something go in a circle is v squared over r. But accept that as a bit of faith, and I'll prove it, especially once you learn your calculus and you can watch that video. And we could do a couple of problems. And this is probably what you care about anyway, but I think it's nice to have that intuition. So once again, let's say we're let's say we're in deep space. Well, let's do a little orbit problem. Let's say that this is Earth. I will do Earth in blue. Let's say that that is Earth. And I have a satellite that is going around Earth. And I'm not going to calculate its, this is a satellite that's going around Earth. And I'm going to do a whole other video on actually figuring out the gravitational force depending on how far away you are from an object. But let's just assume that its gravitational force is similar to what it is on the surface of Earth. And that is a big assumption. Or let's just assume this is a different planet and I'm going to give you the gravitational acceleration. Let's say that the planet, and maybe this isn't Earth, is pulling inwards, right? It always pulls towards its center. And I'll do that in a different color. Let's say it's pulling inwards at 30 feet per second. My question is, what does the velocity of the satellite have to be for the object to stay in orbit? Well, we could just apply the formula, and then maybe we can have a little intuition. So acceleration is equal to v. Oh, and sorry. And let's say that the object is. Let's say the object is, I don't know, 6,000 feet. 6,000 feet from the center. And when we learn gravity, we'll learn it actually. It's the distance from the radius that you're going around is actually relative to the center. Well, actually, it's always going to be, right? Because this is the circle, right? So the radius, this is the center of that circle. You don't have to worry about that. It has nothing to do with gravity. Okay, so the acceleration is v squared over r. The acceleration we know is 30 feet per second. We want to figure out the velocity. And then the radius, I said, is 6,000 feet. 6,000 feet. So let's ignore the units for now. That's making things complex. So multiply both sides of this equation times 6,000. So 3 times 6 is 18. We'll have 4 zeros, 2, 3, 4. So v squared is equal to 18,000. Everything's in feet per second. And so what's v? So v is equal to the square root of 180,000. Let me get the calculator out because I haven't memorized my squares that high. 1, 2, 3. Take the square root. So 424. So the required velocity is 424 feet per second. So if this satellite is at that velocity, it will go in perfect orbit around this planet. Now what happens if the object's velocity is, I don't know, let's say it's a little slower. Let's say what happens, let me do it in different colors so you know what I'm talking about. What happens if its velocity is a little bit less than that? Let's say its velocity is 300 feet per second. Well, then it's not going to be able to travel far enough tangent to the circle well, the way that it'll essentially just do this. It'll always be getting a little bit closer, and it'll spiral in, and it'll hit the planet. And the way to think about this, another way to think about what the required velocity is, you have to go fast enough so that you're always falling in, but every time you fall in, you want to go, in this case, to the right enough so that you're an equal distance. You're still the same distance away from the center, so that your distance from the center never changes if you're going fast enough. And then what happens if its velocity is too fast? What happens in the case where its velocity is, I don't know, 600 feet per second? 600 feet per second? Well, in that case, the object will have enough velocity to actually escape the orbit of the planet. But anyway, that's enough about. I'm actually out of time, so I'll see you in the next video.